Hi everyone, this is Physics 2212 Lab 4, Circuits and Capacitors by Subhan Patel. The purpose of this lab is to examine and study the behavior of components in both series and parallel circuits such as resistors, bulbs, capacitors, and batteries. Second, to examine the behavior of ohmic resistors and capacitors. Finally, to use multimeters to measure the actual values of conventional current and potential differences in the circuit. Here are the formulas used in the lab: Ohm's law, capacitance of a capacitor, loop rule, node rule, formula to compute RC, and the potential difference of a capacitor. You can see the formulas. The fundamental physics concepts used are Ohm's law, the two circuit rules, which are loop rule and node rule, components of a circuit, which you'll see listed, series and parallel circuits, and finally, energy and charge conservation. Well, energy conservation and charge conservation. The assumptions in this lab are that we use wires, ammeters, and batteries that are ideal. That means basically there is no internal resistance in them. Second, the circuit remains entirely functional for infinite time. And finally, the voltmeter is ideal, which means there is infinite internal resistance. That means no current will flow through it. To do this lab, we used the Colorado PHYS project, which we downloaded. So for the procedure for this lab, for part 1, we created a series circuit with 2 ammeters, 1 100 ohm resistor, 1 47 ohm resistor, and 2 1.5 volt batteries. Then we use the same components, but we replace the 1 ammeter with a voltmeter, which you'll see later on. The theoretical value for current we got was 0.0204. You can see the calculations used above the current right here. And you'll see that the experimental was also 0.02 amps. That validates our theoretical value. When the ammeters were reversed, they both still showed 0.02 amps, and the current remained positive. The prediction, we predicted for replacing 1 ammeter with a voltmeter, we predicted that the voltmeter will cause the ammeter to read 0 amps because the voltmeter has infinite internal resistance, and the voltmeter will not allow current to pass through it. And basically, the program showed us that yes, the voltmeter does read 3 volts and the ammeter reads 0 amps. Then we attached the voltmeter to different places in the circuit to obtain the potential differences at each site. The sum of the individual potential differences will be 0 due to the loop rule. That is the round-trip potential difference. Here you'll see the resistances in the circuit. You'll see the experimental values on the side right here, and you'll see the predicted graph. And here you'll see the setup for the next part of the lab, which is a parallel circuit, so that the ammeter is parallel to the resistor, 100 ohm resistor. And this is me explaining that image. The ammeter is placed parallel, in that image the ammeter is placed parallel to the 100 ohm resistor. The ammeter reads 0.06 amps instead of the 0.02 amps previously shown. This increase can be explained by the node rule, which is the current is split with the parallel path and the resistance also decreases, therefore the current increases. Next, we create an RC circuit for this lab using the following components. You'll see 1 9-volt battery, 1 10 ohm light bulb, 1 20 ohm light bulb, and 1 200 millifarad capacitor. And this image shows scenario 1, and scenario 2 will be when the battery is removed and the capacitor will be discharging. Forgive the typo. In scenario 1, as the capacitor charges from the battery, the light bulb will begin bright and then slowly fade to off. And then in scenario 2, which was not shown in the image, the battery is disconnected and the capacitor discharges. In that scenario, the light bulb still begins bright and then fades off as well. In both scenarios, the currents slow down, but the currents are reverse directions in both scenarios, which means the current of the capacitor charging is in reverse direction of the capacitor discharging. The 10 ohm light bulb caused the capacitor to charge in 6.45 seconds and discharge in 9.39 seconds. The 20 ohm light bulb caused the capacitor to charge in 14.07 seconds and discharge in 18.72 seconds. Here you'll see the slope of my time versus natural log of delta V over delta VO and voltage. You'll find RC. So finally, that was the graph for the time dependence was calculated. From that graph, you'll see the time dependence was calculated to be about 6.02 seconds. That is very close to the theoretical 6 seconds, and the percent error was 0.33%. So what if questions? What if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? In real life, the real ammeters would have some internal resistance, but this simulated one had no internal resistance as stated in the assumptions in the previous slides. Therefore, the readings would be less than the values of an ideal ammeter. And the second question is, what if you were doing this in real life and used a real battery to charge a real capacitor with no resistor in the circuit? Well, an ideal model would charge instantly, but the real life model would have a charge time that is slightly longer than the ideal model because the real life model would have resistance throughout the circuit, which would slow down the current, thus causing the capacitor to take more time to charge. Thank you for joining me.